To consider people's decision-making process under uncertainty, probability theory alone cannot provide enough guidance, because we have to think about how people will make decisions about risky events. And our model about people's decision-making under uncertainty better include both the expected value and the risks involved in the outcomes. So for this kind of decision-making process, we have the expected utility model. In general, we calculate the expected utility level from a risky choice and compare that expected utility level to the utility levels generated from other choices, maybe does not involve risky events. And then we can compare these two kinds of alternative using the utility levels to make a decision. So that's how we are going to use the expected utility. How we are going to calculate it is very similar to what we have done for expected value, except now we calculate the probability weighted average of the utility from each possible outcome value. Before, when we calculate the expected value, it's the probability weighted average of the outcome values. Now it's the utility on those possible outcome values. So on the possible outcomes for a risky event, we assign a certain value, call it Vi for the outcome I. And then we calculate using a utility function, this U function here. We put this Vi, that value, into the U function to get the utility yield from that value. And finally, we calculate the probability weighted average of utility levels from each possible outcome value. Obviously, we use the probability for the first outcome to occur to weight the utility that yield from getting the first outcome. For example, let's think about a risky event. The outcome can be either 15 or -5, and each has 50% of probability to occur. So if we use 0.5 times 15 plus 0.5 times -5, we will get 7.5 minus 2.5, the expected value will be 5. However, if we have a utility function that put a utility level of 10 onto this outcome of 15, and put a utility level of -8 on this outcome of -5, then the expected utility is 0.5 times 10, getting from this 15, plus 0.5 times -8, which yields from this -5. We have 5 minus 4, that is 1. So the expected utility for this risky event is only 1. If you put a unit on it, it's so-called utils. That means this person, when choosing this risky event, he only gets an expected utility level of 1 util. Why this utility level is different from the expected value? Because when people assign the utility level onto different outcomes for a risky event, they actually take the risk into consideration. The adverse events, the bad outcomes they don't want to see or they will suffer a lot from, they will put a very low utility level and even a negative level onto those kind of events. In that way, the utility function actually take the risks into account so that when we calculate the expected utility level, it gives us a summarization of the decision maker's consideration of both the expected outcome and the risks involved. Using the idea of expected utility, we can actually classify decision makers' risk preferences into 3 categories: risk averse, risk neutral, and risk loving. Let's look at risk averse first. Consider Irma, an investor who's thinking about buying a stock currently priced at $40, and there is 50% of chance for this stock to reach $70 and another 50% of chance for this stock to fall to $10. So the expected value for this stock is $40. That is 0.5 times $70 plus 0.5 times $10, which is 35 plus 5, give us $40. So the current market price for this stock is exactly equal to its expected value. Let's consider Irma has this kind of concave utility function, which means just like any other concave function, the marginal effect is diminishing. Here, what we are considering on the horizontal axis is the wealth level. So for each additional unit of wealth, you give another $10 and then another $10 to Irma, her marginal utility level will decrease over more and more additional unit of wealth. That's what this concave utility function means. We have said that the two possible outcomes for this $40 investment is 10 and 70. And then the expected value we have calculated is $40. That's the expected value from this investment. But we know that from this utility function, from $10, Irma will get 70 utils, and from $70, Irma will get 140 utils. We take 50% on the 70 plus 50% on the 140, we will have an expected utility level of 105. That is 35 plus 70. We will have an expected utility level of 105. Let's say that Irma does have this $40. With this $40, she can get a utility level of 120 utils. That is higher than the expected utility level of 105 utils. 15 utils difference. Because keeping this $40 yield a higher utility level 120 than making this $40 into a risky investment, getting expected utility of 105. Irma will decide not to take this so-called fair bet, which give you exactly the expected value for your money. This stock investment is a fair bet because it cost Irma $40 to buy this stock, and this stock pays back exactly an expected value of $40. So the expected profit on this stock investment is exactly zero. You pay $40 and it gives back an expected value of $40. Basically, this kind of concave shape in Irma's utility function determines the diminishing marginal utility of wealth for her, and that means she is risk averse. Her utility level on the expected value is higher than her expected utility level from these risky events, so she will not accept this fair bet. For this kind of decision maker, we call their risk preference as risk averse. In most cases, we assume most people are risk averse, basically because most people demonstrate some aversion towards risky events. If we look at this expected utility level, it gives Irma 105 utils. And to get the same kind of happiness level, satisfaction level, Irma only requires $26. We call this $26 amount the so-called certainty equivalent to this risky amount. The certainty equivalent tells us how much the decision maker values the risky event as a sure thing. Point B here is the decision maker's valuation on the risky events, and point A give the same level of happiness, but the wealth level is a certain amount. It's a sure thing. So if the decision maker has this amount with certainty, the decision maker will achieve the same level of satisfaction, happiness, utility level as to have these risky events in hand. In that sense, certainty equivalence can tell us how much the decision maker do not like the risk involved in the risky event. So the difference here between the certainty equivalent amount and the expected value of the risky event that give us this certainty equivalent, this difference is the minimum required compensation for the decision maker to take this risk. You can also say that this is the most that this decision maker would like to pay to avoid this risk involved in this $40 expected value. We call this difference between the expected value of a risky event and its certainty equivalent the risk premium. To get EURA indifferent between the sure thing of $26 and the risky investment with an expected value of $40, the needed risk premium is $14 in terms of expected value to compensate her for taking this risk. Obviously, risk aversion or risk-averse people is only one category of risk preference. There are another two categories. One is risk neutral and the other is risk preferring. The utility function for a risk neutral decision maker is a straight line. That means this decision maker has constant marginal utility on his or her wealth level. For a risk neutral decision maker, the decision made from using expected utility or just simply look at the expected value will be the same, because if you look at the downside event, the adverse outcomes, they don't put a much lower utility level as in the risk aversion case. The result is that the expected utility level will not fall below this utility level from the expected value. That's a result from this straight line utility function. Basically, for risk neutral decision maker, they will choose the event or choice that give the highest level of expected wealth. The risk does not play a role in the decision-making process for a risk-neutral decision maker when facing uncertainty. For the risk-preferring or risk-loving decision makers, they have this convex shape of utility function. This kind of utility function puts higher and higher marginal utility on additional level of wealth. That means the risk-loving decision makers, they have increasing marginal utility on wealth. Here, let's look at the utility level come from the expected value, which is 82 here. Expected value of 40 give 82 utils to this risk-loving decision maker. For the risky event, if the outcome is 10, the risk-loving decision maker will get 70 utils. And if the outcome is 70, this decision maker will get 140 utils. So the expected utility will be 50% times 70 plus 50% times 140. We get a expected utility level of 105 again. This 105 utils is higher than 82 utils. So this risk-loving decision maker will definitely choose the risky event than this sure thing of $40. You can really attribute this result to the fact that this decision maker, when facing this $70 outcome, this decision maker put an extremely high marginal value on it. And that's basically the property of this convex shape of the utility function. So with this convex utility function, this risk-loving decision maker will have expected utility levels from risky events that are higher than their utility levels on the expected values for these kind of risky events. and they will always choose the risky events instead of the wealth level with certainty. That's why we call them risk-loving or risk-preferring, as in the textbook. The concave and the convex shape can help us to understand the properties of the value function in prospect theory, which is an important part of behavioral economics. I have put a link to a lecture video presented by Professor Robert Schiller from Yale University on prospect theory, and you should watch it on Blackboard. The value function in prospect theory is some kind of utility function. But this value function is not defined on wealth level. Instead, it depends on the gains or losses from a reference point. In the middle, the reference point is 0, and people compare their outcomes from where they are standing. That's the reference point. So if there are gains, we are in this positive region. If there are losses, we are in this negative region. And we can see that we have a concave shape over the gains on this value function and a convex shape over losses on this value function. So over gains, people are risk averse, and then over losses, people are actually risk loving. This is a very different conclusion from expected utility theory. And in most cases, the prospect theory gives a better description than the expected utility model about what people actually do when facing choices under uncertainty. One thing we have observed about stock investors' behavior is that investors in stocks usually sell their winners too early. That means people prefer to convert their gains into certainty, even though there is still additional upside possibility for their stocks. They just like to convert the risky investment into a certain amount. We also observe that stock investors often hold on to their losers for too long. If they're losing money on the stock, they just hold it and hold it, hoping for the stock to come back. So people actually prefer to hold on to the risk exposure when facing possible losses. And what they're hoping for is basically for the loss to be reversed. So stock investors often ride their losers for too long. They are risk-loving when facing losses because they would like to delay the realization of the uncertain losses and still hoping for the recovery of their losses if there's a chance for the stock to come back. So even though the prospect theory and the expected utility model are two different theories for making decisions under uncertainty, they still share similar concepts such as risk aversion and risk loving when describing people's risk attitudes.